Okay, good morning, everyone. So, together with my colleague, Dr. Ioannis Nikolaidis, we are going to talk about localization using 5G data. So, both of us are with the Department of Computing Science, and today we have the graduate student who also worked on this project and did the heavy lifting, so Jihoon. I'm going to talk a little bit about what he has done during the presentation. So let's start with the problem first. What problem are we trying to solve? So, um, of course, this is trying to use localization, meaning that we want to understand where people are inside and outside buildings. And 5G enables us to do that, as we'll see. But really, the reason that we are interested in this is to enable higher energy savings in buildings. I've been working on this problem since 2015. Buildings consume a lot of energy, and this is because of the fact that they are conditioned not based on the actual occupancy patterns, but based on the intuition of the facility manager. So, in many cases, this is good, meaning that the facility manager knows exactly when the building is occupied, how many occupants are there, and how much heating or cooling is needed in order to run the HVAC system or other subsystems that we have in the building. But in some cases, intuition is not good. So we need to actually use real-time data in order to save energy in buildings. And that's how this project started. So we wanted to improve localization. And as you see on this slide, um, saving energy in buildings, running the HVAC system in a more optimal fashion is the main goal. And this can be done using reactive and proactive control strategies. Like, for example, we can have machine learning techniques used for controlling the building, reinforcement learning techniques that are used for controlling the building in a safe and optimal manner. There are other applications that rely on real-time occupancy data. Eleni did a great job in the previous presentation talking about path planning inside the building. So if you are a visitor maybe to a commercial building like a hospital, and this is the first time that you are in that building, you are in distress, it's very hard to find the room that you want to go to. And this technology can help you actually find your way to that particular space. So that's another use case for this, but there are many other things, evacuation planning, asset tracking in warehouses, and other things that are enabled by this technology. So that's basically the problem. Now, of course, there are many different ways that you can get a better understanding of building occupancy. This can be done using data you gather from sensors, occupancy sensors you have in private offices or in public spaces in the building. In the previous slide, I had this diagram by Enlighten. It's a company that actually has these occupancy sensors. You can install these sensors in private offices and you get a sense of how many people are there or whether the offices are occupied or not. But it can also be done using virtual sensors. And the reason I'm saying that these are virtual sensors is that because they are not actually deployed there to get a sense of the occupancy state of the space. These are perhaps Wi-Fi access points, 5G antennas, cell towers that are there in order to provide internet access to people. But we can use this data to get a better understanding of the occupancy pattern of the building. So this can be done using different approaches, Wi-Fi, GPS, and cellular technology, 4G and 5G. And of course, GPS works very well outside the building, especially in not very dense areas, not in the core of, for example, a city. GPS works very well, but when it comes to densely populated spaces, GPS lacks precision. The same thing can be said for indoor localization, as we'll see. The other thing that can be done is using Wi-Fi. Wi-Fi works very well when you are inside the building. There are multiple Wi-Fi access points. You receive these beacon frames from these Wi-Fi access points, and based on the received signal strength, you would be able to understand how far people are from these access points. Use this for localization. But again, Wi-Fi alone is not going to solve the problem for multiple reasons. One of them is that there's not a one-to-one mapping between the Wi-Fi cells or the areas where you can actually see the Wi-Fi access point and the thermal zones in the building. So we need more than that. And finally, you can also do localization using 4G LTE or 5G cell towers, and this can be used to enhance the accuracy of other technologies that we have. So the goal of this project was to explore whether location estimates from these different technologies can be fused to improve the accuracy. And then we faced a lot of different challenges. So the most important one was that we needed to basically collect data. So Jihoon was the graduate student who had the private SIM card, and for the 5G private network, he went around the main quad in the main campus of U of A, and he tried to collect data to understand basically receiver signal strength and use this data to build this map, RF propagation model that we need. But this cannot be done for every space. It's very costly. We need to send people there, right? So would it be possible to improve the accuracy using simulation in the loop? And we'll be talking a little bit about that, how simulation can enhance the accuracy of 5G localization. And when we talk about using a simulator, of course, the model must be calibrated. If the model is not calibrated, then it's not going to be very useful. So that's the first challenge. The second one is extracting and incorporating cellular information. This can be very fine-grained or it can be coarse-grained information. So if you have access to Wi-Fi, or 5G cell towers, so of course you can use physical layer information, but this information is not always exposed. So that is another challenge for our project. And finally, there is something called geolocation API by Google. Google already fuses data from multiple sources, including Wi-Fi and other types of sensing technology that they use, but we don't know how it works. So would it be possible to improve upon that by using 5G, Wi-Fi, GPS, depending on the location and taking into account the uncertainty of these location estimates? So these are the challenges that we faced. And in order to do this, we use the digital twin model of the campus. So this is done using a library called Siona, developed by NVIDIA. It's a very useful and powerful tool that enables you to build this map and understand ray tracing simulation, be able to do modeling of RF propagation in the space and whatnot. So I'll hand it over to Yanis to talk a little bit about the results that we got from the simulation.
Okay, thank you, Omid. Stepping back for a moment, there are a few elements in this project that come into play. One of them is thinking in terms of what would be the service at the end. And we mentioned already about Google location services. How do you bid it? And how you bid it is to actually have something that's super localized and eventually something that works very well for indoor spaces. Now, in tying in with the idea of the digital twin, we would like to use the digital twin of a campus, both outdoor and indoor, to actually inform the models that we're using for the localization. Until relatively recently, the idea that you would have, complete ray tracing models for the wireless propagation on a big campus or inside buildings was rather computationally prohibitive. So that's where tools like Siona, for example, which of course they leverage the power of GPUs today, come into play. The aspects that are simulated here can then be matched to what we have measured in the real environment. And by aligning the two, we can then make predictions based on the simulated models. So both the data collection side, which is labor intensive, can be mitigated. And then the quality also of the results can be tuned if we want better quality results, better localization. We might actually engage in a more accurate both simulation and surveying of the space. Oh, the other way. Just to give you an example how the processing pipeline works, from the side of Siona, what's needed are the buildings. Description of the buildings, we already have seen this in the presentation given by Eleni. OpenStreetMap, again, was a lifesaver here. But keep in mind, for the indoor spaces, we also need the indoor space models. And the models are easy to import. There are aspects to those models, though, that remain to be explored further. For example, be the place that we are here in Edmonton, we should simulate snow cover. We should also simulate the foliage, the existence or not of the trees in full bloom or completely naked of leaves. So there's more to be explored definitely on the side of the simulation. So I'm going to show you something which is an approximation, some results that we got when we tried to match the measurements we were getting, Jihun was getting, roaming around, versus to what we could get from the simulator. Now, I had done this in the past, and the results were relatively atrocious. So it's rather surprising that what we can do with the simulation today is very close to reality. Okay, eventually I'm going to get used to it. I have no idea how to activate this animation. Just a click. Oh, you can see it. Maybe. I'm actually, plus I'm a bit blind, so. Oh, there you go. The real track is the yellow line, and the one that's derived using the data, the measured data, is the dotted white line. Now, of course, they don't match, but the average localization error was in the 42.3 meters. Now, this sounds horrible, but that's not GPS, right? So we're still doing okay. Now, what was important is to match this number with a number that we get from the simulator. And there is a slide that's missing, we should have here, which would demonstrate precisely that we got the same average localization error using just the simulator. Now, what's in that simulator, other than the open map, the buildings, is is the orientation of the antennas. So we know where the cell towers are placed. We know also what their azimuth is. And we're using relatively easy information to extract from any cell phone out there. So this doesn't have anything particularly interesting in terms of capabilities of measurements that we could acquire. But when we add to that the full force of measurements we can get out of the 5G infrastructure, and in this case, in the simulated setting, we reduced the localization error to 6.93, where previously it was something close to 40 meters. Now, you might not be enthusiastic about it because you have seen GPS localization giving you something the same order, but there was no GPS involved here whatsoever. So in the outdoor space, we're actually matching more or less the performance of GPS. Now, the next step, the important step, is what happens with the indoor environments. Oh, okay, that's a sudden transition. Well, here it is. The first one is really to investigate the results for indoor localization. And again, as I mentioned before, the idea is to use our approach as a refinement layer on top of a service that's already out there, which is the Google Fused localization. And making it effectively a super localized form of localization for buildings or areas whose models are known and they're installed in for example, the mobile edge computing platforms. The subsequent direct application, the one that Omid talked about, is the identification of the occupancy in the various zones within the buildings and the transitions from indoor, outdoor, and vice versa. So large flows of and movement of people in the particular directions, crossing the zones that are meaningful from the HVAC operation point of view. With that, I will invite my colleague to provide some more concluding remarks.
Sure. So I think that's basically the next step for us. We would like to understand what happens as people move indoors. And I want to thank Tracy, who is with us today from the facilities and operation team. We were very fortunate to work with them, and this was the main reason that the project was successful. We are hoping to do this on campus in different buildings, and University Commons, which is the new building that we have on campus, and it will be the CS department house very soon. It's basically one place that we could use this technology to have or make real impact.
So thank you all for participating. This is really cool. I don't know how many of you have seen the University Commons building, but it is a real showcase. And you know, I don't think before this I truly appreciated how much tech sits inside that building. But I think it's really great that we're able to use it as a bit of a living lab. You know, which fits with the 5G project that we're talking about here today. Around that. So maybe if you can just talk a little bit about, you know, how you got involved with that building in particular, and like, and a little bit maybe more about the building. Tracy gave us some context about the building, but you know, what else is possible with that building?
So the intent for the design of that building, which is 100 years old, was for us to be able to create the infrastructure and the systems to make it last another 100 years. And so from the perspective of a 100-year-old building, you can imagine a fairly porous building envelope. And so fundamentally, we needed to bring that up to the 21st century standards, which was by no means simple. And so to start with that building envelope and to bring some of the technology to make that as a nice airtight building as possible with 400,000 square feet was not simple, and took a good deal of cost benefit studies to make sure that we could get that nice balance of what we needed to do. And then the ventilation for a building of that size, as you can imagine, is massive. And so the systems that we brought online for that actually had a very high performance heat recovery systems in there to be able to maintain and sustain a lot of that building energy within the building and reuse it, even though we're bringing in 100% fresh air. So very, very high performance ventilation system, and the air quality is quite high and should sustain that high quality for the life of the building. So comfort is an important thing. We also have the benefit at the campus of a central plant we have chilled water, and we have heated water that we can utilize for our systems. So we have very low, I guess, cost of actual energy per square foot in that building, which really helps in a large building of that size. We have lighting control systems that are smart with the occupants that are in there. And although it irritates people when they're sitting in their desk for 20 minutes and the light turn off, still very efficient technology that we're using. There's a number of building access systems for only those with, I guess, credentials to be able to get into certain areas of the building. There's a lot of technology in that big building, and it's very exciting to be part of that process and that project.
And Ioanis and Omid, how did you connect with the building folks? Like, what does that process look like, you know, from a researcher getting connected with, you know, a new build? That's, tell us more.
Yep. So together with Eleni, we had this CFI grant, and this enabled us to basically invest and buy a lot of sensors battery storage system that is installed in the basement of this building, rooftop solar panels that we have in this building. And this was the start of the project because once we got this grant from Innovations Canada, we were able to start working on this building. We engaged different groups on campus, and facilities and operations were very cooperative, and we were fortunate to have Tracy as an advocate of this project in their team. So we were able to collect a lot of data. Tracy talked a little bit about all different systems and sensors that we have in the building. But one thing I want to emphasize is the fact that we have renewable generation, on-site renewable generation and battery storage system in the basement. This enables a lot of new applications, including using solar energy to basically run building systems. And if you add occupants to that equation, then you would be able to optimize the whole building operation using real-time intelligence that is driven by the data that we get from all the sensors and wireless technology as well.
You want to add something?
Well, my side to this is that I generally like to play with sensors, and people come to me whenever they have a sensors-oriented problem, and I engage with them, and that's how it happens. But more specifically, I had worked almost a decade ago on a project in the north. It was in Fort McMurray. And it was the complete instrumentation of an apartment building there, which was employing many heat recovery systems. It was employing geothermal sources as well. Just getting the quality data to understand the behavior of the building throughout the seasons turned out to be a very interesting exercise. And back then, we were not really concerned as much about the occupant behavior. So I think what has changed, and actually has changed the way I look at the research, is I'm looking at the individuals and how they're interacting with space, with the movement, the flow of people, and therefore what would be ways that you can optimize both the use of resources and also have some ability to improve the comfort in those environments.
So talk a little bit about, you talked about the positioning of people, and getting that more accurate. So how is that going to advance sort of building construction going forward?
I think I'll do that one, Ioanis. So, and it's a really interesting question because as we build our models during the course of design, it is done typically in 3D. And then the industry, as slow and pokey as it is, will revert back to drawings and let everybody sort it out. And so what we did at the University Commons and subsequent projects is we utilized that 3D model to virtually coordinate all of the building systems that are up in the ceilings, in the floors, below the floors, in the walls, before we actually build it. And then we used the model to construct it. So we did not abandon all the work that went into that design work. And we actually implemented that in the field, and our construction teams have zero rework. And so it is being embraced by our teams, our trade partners, as a very efficient way to go about using a digital model. And then we don't abandon that model. We then use that data-rich model for facilities management afterwards. So it is a full life cycle model use now, and it has not been in the past.
So, and then talk a little bit about, because the university in particular, I'm aware has lots of old buildings. How does this apply to retrofits of buildings and sort of, what can you do with an existing building without sort of ripping out all the walls and putting in everything brand new?
Yeah, I can maybe speak to that a little bit. So one of the things that we are doing in this new building is that on one floor, which is the seventh floor of the building, we have lots of occupancy sensors, and these are not wireless, basically access points or other things. They are occupant sensors like cameras and whatnot. So basically, we get a sense of how many people are there and so on. Of course, addressing privacy concerns and anonymizing this data and so on and so forth. But we have this data, and then on other floors of the building, we don't have these sensors. We are relying only on basically Wi-Fi access points and 5G antennas that we may have indoors. So the question that we are asking is how much we get from these sensors that are very expensive to buy and install, right? In addition to existing wireless infrastructure that we have in the building. And if the answer to this question is that there is not a significant gain, right, then this can be used readily in almost all legacy buildings that we have on campus today, because wireless is widely available. We have Wi-Fi infrastructure on campus. We have 5G, 4G antennas. So it could be done in every building, and we don't really need to go through this process of buying sensors and installing them, which is very costly.
And just to add to that as well, the legacy buildings are going to become easier and easier to digitize. The technology is surely catching up and moving quickly. Not maybe as quickly as these gentlemen are moving, but to literally take scans in the field and digitize those and turn them into a replication, whether that be a mesh or a model, is happening a lot more faster and a lot more economically than previous. And so to turn campus into a digital twin in its entirety, it's not that far of a stretch.
So, and you know, we all don't live in these big commercial buildings. What about residential spaces? Like, is there where does this fit in the future for our homes?
So I can maybe talk a little bit about that, and Yanis can maybe add more. So in the residential space, a lot of companies try to do this. We had prototypes of different types of sensing systems that were developed maybe 15 years ago. And most companies failed in that space. There are lots of reasons for this. The most important thing is that in terms of savings for the end customer, the cost benefit analysis shows that basically there is not a lot of savings. And the return on investment, if you do the analysis, you will see that it's basically a couple of years, right? And who knows whether the occupants will be living in that space for that period of time. So it's a little bit difficult to do this in residential buildings unless like electricity becomes really expensive. And at that point, this will result in like these technologies being adopted in the residential space. In the commercial space, it's easier. And the main reason is that it's not just about energy saving, it's also about comfort and productivity. So I've been talking to companies like Schneider Electric and Siemens and other big players in this space. And what I hear from them is that productivity in the office space is the key thing for them. So they don't really want to do a lot of energy saving. Of course, this is great, and we want to run buildings in a sustainable fashion. But more important than that is having a healthy environment where, people are more performant, and the productivity goes up, and this will have a real impact for the company. So I think that's the main reason that it wasn't very successful. Of course, there are integration challenges and other things that maybe my colleague we'll talk about.
Well, the one thing I would like to add is that there's definitely lots more monitoring of the residential environments. People have their smart thermostats and what have you, and they even have their phones parked around most of the time that could do some of the analytical work related to understanding the degree of comfort and so forth. So I think what's really difficult in that space is making an informed decision of what action should the homeowner take next? What is the objective? Let's assume that they always want to have, pay less for electricity or whatever. What is the degree of analysis that's necessary before we can provide some information, for example, figure out about the insulation or the windows or something, or there's some usage pattern. So I think it becomes to be very subjective, and that gets in the way of having a more, let's say, regulated, more controlled environment than the commercial buildings or large residential buildings.
Great. Well, I think we're pretty much out of time, but thank you so much. I'm really excited that you guys described value as far more than monetary, because I think that's a really important thing as we think about moving technologies forward, that we have to look at this not just from a simple cost basis, but looking at other things as well. So I thank you for doing that, and thank you for sharing your experience and for working on this project.
Thank you.